Hello, ladies and gentlemen. We are going to do a problem with conservation of energy. A 40-kilogram child is sitting at the top of a playground slide. The slide is 4 meters long and makes an angle of 30 degrees with the horizontal. If friction is ignored, how fast is the child going at the bottom of the slide? Well, I'm going to use energy, and at the top of the slide, what kind of energy does this child have? Potential energy. And how did this child get that potential energy? He or she did work by climbing up the height of the slide, and the work that was done climbing to the top is now stored as potential energy. When the child slides down, the potential energy is going to transform into kinetic energy or speed. And I want to know how much speed at the bottom. So I'm going to say potential energy at the top is going to be equal to kinetic energy at the bottom of the slide. How can I get away with doing this? Friction and losses to friction are going to be ignored. Now the potential energy at the top is going to be the mass, the height, the acceleration of gravity, and at the bottom, 1/2 mass velocity at the bottom squared. Now a couple interesting things are happening in this problem. One of the things that's happening is you'll notice there's mass on this side and mass on that side. Actually, mass can drop out of this equation. You don't have to, you can carry it through if you want, but I am all for anything that makes life simpler. So I'm looking for velocity. This is the term I'm after. I know gravity, but I've got to find height. Here's the cool thing about conservation of energy. We care about the displacement from where you end to where you begin in whatever force field you are working against. So the difference from here to there is actually just this height. We don't care so much the actual path that was taken. We don't care if this slide was a humpity-bumpity kind of a slide or a nice smooth slide. As long as we can ignore friction, we can just use this beginning and ending altitude in order to determine height. So I'm going to take this triangle and use this to make height. I've got 4 meters as a hypotenuse, 30 as an angle, and my height is going to be the opposite side. So I'm going to use sine. Opposite is going to be my hypotenuse times the sine of theta, or 4 meters times the sine of 30 degrees, and this is going to be 2 meters. So the actual height here is 2 meters. Now I can rearrange this and put some numbers in. So the velocity at the bottom is going to be 2 times height times acceleration of gravity. This is velocity squared. So I'm going to square root that. And what I'm going to end up with is 2 times my 2 meters times 9.8 meters per second squared. And when I take the square root of that, I ended up with 6.26 meters per second is the velocity at the bottom of the slide. Now that's the first part. Part B gets a little interesting. Part B says, what if there is some loss to friction, and we actually measure the fact that when the child gets to the bottom, they're not going this 6.26 meters per second that's predicted. They're only going 5 meters per second. I want to know what percentage of energy has been lost from the top to the bottom of the slide. So the potential energy at the top would be equal to the mass, the height, the acceleration of gravity. So I've got a 40-kilogram child, 2 meters vertical height, 9.8 meters per second squared. So the energy at the top ends up being 784 joules. Now, due to friction, the velocity at the bottom is actually measured to be 5 meters per second. So what is the kinetic energy at the bottom going to be? 1/2 mass velocity squared, 1/2 my 40 kilograms for my child, 5 meters per second squared right there, and I end up with a kinetic energy at the bottom of 500 joules. Now the question was, what is the percent energy lost. Now, I'm going to find the percent of energy that is kept, or in another word, I'm going to find the percent efficiency of the system, and then we're going to subtract to find loss. So efficiency is output divided by input. So at the times 100. In the beginning, at the top of the slide, there was 784 joules of input. At the bottom, there were 500 joules left. Times 100, what that means is my slide was 63.8% efficient. So if I want to know how much energy is actually lost, if I take 100 minus 63.8, that means 36.2, or over 1/3 the energy, is lost. And the difference in velocity was 6.3 meters per second compared to 5 meters per second. Well, how in the world can you have such a huge loss of energy and you have a very small change in velocity? And remember, we talked about the fact that kinetic energy is proportional to velocity squared. A small change in velocity, big change in energy.